think we're recording now. Okay. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I'll be going over some commonly asked mathematics questions at both the high school and college level. If you need some help with your homework or if you need some tutoring, check out the links in the description below. Awesome. So today, we will be doing a lot of math. Mathematic magic. Let me just switch over to my screen. Boom. Just like that. And let's get it going. Okay. So the first question that we got on the menu today is how do we solve ln of x is equal to 2? Ln of x is equal to 2. Well, an interesting property about ln is that ln is basically saying what's in here, this is the argument that you pass to the logarithm. Now to get that out of the logarithm, to pull this out, raise to the power with the base. What that means is to extract x out of ln of x, we would, on both sides of the equation, what we have, like the ln of x, and as well as the 2, that is going to become the power of the base here. Now the base of this, ln of x is the same as logarithm of x, but when the base is e. And e is equal to 2.718, on and on and on and on. Yeah, so since we don't really like writing, because it goes on and on forever, kind of like pi goes on and on forever with all those different decimal points. So we write e instead. This is a very special number, Euler's number, from a very smart mathematician named Euler, who discovered this, trying to figure out some stuff about compound interest. So keep this in mind. And in this case, our base is e. So to get x out of the ln of x, what we would do is we raise it to the power of the base. So if the base is e to the power of ln of x, remember, do that on both sides of the equation. E to the power of 2, or e squared. Okay, so these like neutralize each other, like the ln and the base of e for the power. So that just becomes x equals e to the power of 2. Now it'd be perfectly reasonable to leave your e as just to the power of 2, just looking like this. So that's perfectly reasonable. Okay, sounds good. Did they come to the same conclusion here? Yep, so they know that to pull out the a, you just got to raise them to the power of the base, and that will neutralize the ln. That looks good. X is e to the power of 2, e squared. Of course, you could calculate that to like an actual decimal, but you know you won't be able to. It's better to leave it as e to the power of 2, because we know that that's like a precise value. But if you do the decimal and actually expand it out, it would be a rounded value, which you know, sometimes you need a lot more precision. So it's good to keep it as its mathematical definition, e to the power of 2. So the above solution is correct. Awesome. Okay. The next thing that we want to cover today is how do we find the sum of the arithmetic sequence 1, 3, 5, 7, 9, counting up by 2's all the way up until we get to 27. Sum of all these terms. Okay, and we're trying to find the sum. Now the partial sum of an arithmetic series is the following equation. So we know that we can say S for sum is equal to n over 2 times I'm going to use the other equation that they have. So, okay, it's n over 2 times the first term, a1 plus an. That's the first term. And that's the last term. Okay, now this is a very special equation because this will always work out. But okay, we know the first term. Let's just call our first term A. Whoops, I need to put my glasses on because I wrote last as the first and first as the last. Uh-oh. That's not good. So that's first. And this is the last term. Yep. Now, let's list out what do we know about our terms. So we know that our first term, A1, is equal to 1. Our last term, in this case, we can clearly see that it's 27, but it's not always going to be the case. So to calculate the last term for an arithmetic series is, well, the key thing about an arithmetic series or sequence is that, like, you're always adding by the same number every time. In this case, it's plus 2, plus 2, plus 2. So that is our increase each time. That's typically represented by the variable d. So increase each time. D is equal to 2 in this case. And the last term, the nth term, because we need to know, like, n, which is like which term it is. Last term is an. That's equal to the first term, a1, plus n, which is like how many terms there are. Is it n minus 1? I think it's n minus 1, because like the second term you're only increasing by 1. I think it's n minus 1. Yep, they have n minus 1 multiplied by the increase every time. So the second term, n is equal to 2. 2 minus 1 is 1, so it's just a plus the increase. So it'd be like the increase is 2. So yep. And if you just try like the fourth term, n equals 4. That's n minus 1. 3 times 2 plus the first term. Yep, it makes sense. That would be the value of the last term. And we know that the last term number here for 27 is last term value is equal to a of n, which is equal to a1 plus, or it's literally written just here, but to sub in the a1 and the d values, we can solve for n. Because, like, let's say if that term was like 200,001, it might be difficult to like count them individually. We can math it out. It'll be a lot easier. So a1 is 1 plus n minus 1. We don't know that yet. We're trying to solve for n, and we know that d is 2. Okay, so 27 minus 1, all of that times 1 over 2 is equal to n minus 1. Okay, um, so that's 1/2 of, so 27 minus 1, that's 26, and divide that by 2, 13. 13 equals n minus 1, which means that 14 is equal to n. Okay, that's the first thing of interest that we need. Our last term, a of n, is 27. We know that. That's something interesting that we should keep track of. We know that d is equal to 2, and we know what the first term is. Okay, actually, we only need, to use this equation, another way you can write the equation, if you don't actually know what the last term is like this. N over 2. You're always pretty much going to need to know what the first term is. So a1 plus, well, let's sub out the last term, an, with what it's equal to here. So that's, let me just get a little bit more space. Un peu plus d'espace, oui, oui. So that would be a1 plus n minus 1 d, which is equal to n over 2. Well, we can just remove the brackets. So it's 2 a's, 2 a1s, plus n minus 1 times d. So if you don't know directly what the last term in that you need to consider is, like if it just says like find the sum of the series from the first term all the way to the 25th term, you don't actually need to find out directly what it is. So yep, use these different equations whenever you feel comfortable. Just gonna draw some separation. Okay, so we know a1, we know an, 1 and 27 respectively, and we know n, we calculated that to be 14. So let's stick that in the equation and figure out what we're gonna get. Let's do it in blue, because I like blueberries. Equals, well, n, that's 14 over 2. And then a1, what's a1? That's just 1. An, the last term that we're looking at, is 27. 14 divided by 2, 7. Quick math. 1 plus 27, 28. 7 times 28, according to my, let me pull out my calculator, because my mental math is not the sharpest in the shed, but we found the answer to be 196. Awesome. So the sum of the sequence between 1, 3, 5, 7, all the way up to 27, counting by 2, the sum of all that, 196. And yeah, I actually am pretty confident that's the case. You could check it yourself. You could do 1 plus 2 plus 3 plus 4 plus, 1 plus 3 plus 5 plus 7 plus 9. You can add them all up and you would come to the same result. But use the equation. It's a lot easier. Okay, so they came to the same conclusion, but I guess they, Yep, used the same equation, came to the same conclusion. And we can share the same satisfaction of getting this question all good. Okay, so the above solution is correct. Okay, so the next question that we got on the menu today, what is x plus y to the power of 3? What is that? Now, I know it might be a little bit tempting to say that, hey, what's just x cubed plus y cubed? No, absolutely wrong, not even close. That is an extremely dangerous mathematical mistake. If you make that, you will get in trouble and you will deserve it. So when we say x plus y is to the power of 3, what that really means is x plus y times x plus y times x plus y. Okay, now this is not even close to what that is. So get that mistake out of your head. If you make it, well, you're gonna have a bad time and you're gonna deserve it. So we have the cubed to the power of 3 is also referred to as cubed. If you have x plus y cubed, you can rewrite it like this, and then we can just treat it as if we're multiplying terms together. Now keep in mind that I'll just show like what we got to multiply. So first you want to multiply like the first term of the first one with the first term of the second. Then you want to get the first term of the first and the second term of the second. And then maybe in blue we can have the second term times the first of the second. And purple for that one. We'll just like hold off on doing the last one here. For now, let's just do them like 2 at a time because that's nice and easy. Now keep in mind we have to we're basically going to add up all of the possibilities that they can multiply together. So like first and second, first and first, and second and first, second and second. Sounds good? Cool. So let's write that out in on the next line. So the red ones is x squared. Okay, now the next one was green. So that's plus xy. Okay, now the next one was blue. So that's plus yx. That's the same as xy. We can add these two together. And then in purple, we're going to have y times y plus y squared. Now keep in mind all of these are positive, so we're going to have positive answers. But if any of those was negative, we might see some negatives in your answer. Okay, and x plus y, because we left that there and we didn't really touch it yet. Okay, so let's combine the xy plus the yx. That's just 2xy. So that will just be x squared plus 2xy plus y squared x plus y. Okay, and now we're going to do a similar type of multiplication out of these terms. Just going to shift them down. We get a little bit more space. Okay, now starting with red. Pretty much going to be doing the same process like everything. We have to add up the sum of all the possible combinations at which every term here can be multiplied together. Okay, so that's going to look a little something like this. Maybe the first one we're going to have x squared times x, and then we're going to have red. What's next on the rainbow? Orange. You can have those two multiplied together, and then the next one, yellow. Actually, not yellow. Yellow's kind of hard to see. Next two things that we want to multiply together would be like this term, the 2xy, plus and multiply with x, and then we multiply that with the y. And the last term we can do in purple. The y squared has to be multiplied with the x, as well as with the y. I'll just make it a little bit curly to make it, special. It's always good to be special. Okay, so let's write out this equation. So the red things multiply together. That's just x squared times x. So that's x cubed. Next thing was the orange. X squared times y. They're all positive, so x squared times y. Fairly straightforward. The next thing was green. So that's 2xy times x. So that's plus 2x squared y, because there's two x's and one y and one 2. The next thing was blue. So 2xy times y, so that is plus 2xy squared. And then next thing was the purple. Y squared times x plus xy squared. And the last one was in gray but curly. I'm not going to draw these out curly, but plus y cubed. Okay, so let's see which terms we can combine. You see these two? Those are both x squared y, so we can add those together, and these are very similar, so they both xy squared, so we can group those two together. And our final answer is going to look a little something like this. So we're going to have the x cubed all the way at the front plus 3x squared y plus 3xy squared plus y cubed. And that would be our final answer. So as you can see, this is much different than what we had initially up here. Yeah, not even close. We're missing 2 whole terms. So don't make that mistake. You'll be in trouble. Make sure, like, if you see something cubed, or to any power for that matter, like, you know, think about what it really means. It's where everything between the brackets is multiplied with itself like this, expand it out, and you'll come to a conclusion like this. Sounds good? Good. Yeah, it seems like they came to the same conclusion. Looks good. The above solution is good. Okay, the next question that we got on the menu today is if y varies inversely as x. And okay, let's write that out, what that means in a mathy sense first. So y varies inversely as x. What that means, or to write that out as a math relationship, you say like y alpha, which means is proportional to 1 over x. It means that if y gets big, x is getting small. Or if y is getting big, or if x is getting big, y is getting small. Okay, but what this really means is that y is equal to some constant times, let's call the constant k, because constant starts with k. Yep, makes sense. 1 over x. Oh, I know constant doesn't start with k, but why do mathematicians want to use k for constant? I don't really see why, but you know, I guess they were using the c for something else. Not to worry, we know how to treat it. So yeah, we also know that y is equal to 8. Y is equal to 8, which is equal to k times 1 over 4. This is when x is equal to 4. That's what we're getting over here. Y equal to 8 is when x is equal to 4. So this should help us find what k is, what the constant is. What constant is what's the constant of their inverse relationship? So we can actually solve for that if we multiply both sides by 4. So that'll be 4 times 8 equals k. Oh, not multiply k, equals k. What's 4 times 8? 32. Oh, that makes sense. If k is 32, that means the right side is 32 divided by 4. Yep, sounds about right. Does the solution say that? Yep. Okay, so So we know what k is. So we know that y is just equal to 32 divided by x. Okay, so if the question asks, what is y when x is equal to 16? X equals 16. That means y is equal to 32 divided by x, in this case, 16. What's 32 divided by 16? 2. Solid 2. So when x is equal to 16, y is 2. And that's 2 true. Yeah, so that's how you know it. I think what's the key word here is like setting up originally this equation y equals k over x when you know that they have an inverse relationship with each other. And the alpha here just means their relationship is inverse, but you can easily convert that alpha into an equals a constant times whatever. Awesome, sounds good. They said y is 2. That's 2 true. That's good. So the above solution is good. Okay. The next question on the menu today is, are negative numbers rational? Numbers rational. Before we ask what if negative numbers are rational, let's figure out what is a rational number. Okay, rational numbers are numbers that can be represented as a ratio between two integers. So numbers that can be represented as a ratio between two integers. Now, what is an integer? An integer is a number without a decimal part. Okay? Without a decimal. Some examples of integers versus not integer. Maybe some integers that you're familiar with. 41, -7, 0, 23. Those are all integers. Something that is not an integer, 1.5. Yeah, not an integer. It's got a decimal part. No decimal for integers. Pi. Definitely not an integer because it's like 3.141592565 numbers on my mind. Whatever. It's got decimals. It's not a rational. It's not an integer. Okay. So if a rational number can be represented as a ratio between two integers, I'll just like square this off. So it's kind of like a separate idea. A rational number is basically just something where you're able to find rational is equal to integer over integer. So an example like 5 is definitely a rational number because, well, you could represent it as an integer divided by another integer. You can do it like equals 5 divided by 1. That would be an example of a rational number. 3.3 repeating is a rational number because you know that is 10 divided by 3. 10 and 3 are both integers, the ratio between them will make a rational number 3.3, but the 3's repeat many times, infinity many times. Now, we know that it just has to be an integer on the top and the bottom. Now, let's say if we put a negative number on the top, the result will always be negative if the bottom is positive. So let's say we have like negative 7 over positive 11. The result of that is going to be a negative number. It's going to be negative 7 divided by 11. Probably should have chose something that I could do off the top of the dome. 7 divided 11. Negative 0.6363, on and on and on. Yeah. So this is just an example. Like if a rational number, the definition is just an integer divided by another integer. And we know that integers are allowed to be negative, positive, like, you know, negative 7 is an example of a negative integer. One integer divided by another integer, if one of them is negative, even if the bottom is negative and the top is positive, you can get a negative rational number. So are negative numbers rational? Only if they can be represented by the ratio of two integers. There are some negative numbers that are not rational. I can't say that every negative number is irrational, is rational. Like I know that pi is irrational, I think. I hope so. Yeah, pi is certainly irrational. So that means like negative 1 multiplied by pi is also irrational. That's a negative number, but it's not rational. Being negative alone doesn't make you rational. Being an integer divided by another integer is what makes you rational. But being negative alone doesn't make you rational. So negative numbers can be rational, but there are negative non-rational or irrational. So, yeah. Okay, I'm just going to write that in as a comment. The above solution is correct. Maybe some info that negatives rational would be a little more clear. Okay, cool. So we can move on to the next question that we got. Okay. Next question that we got on the menu today is, how do we factor out x cubed plus 1? We gotta factor that little equation. Okay, I guess we can put brackets around it. Doesn't really matter. Now, this is one of those situations where we want to use the difference of cubes. So anytime you see where you're trying to factor out things and hey, it's two terms added together and both of them are cubes of something, like x to the power of 3, that's clearly x cubed. 1, well, that's 1 cubed. You can pull something like this, the difference of cubes, and this will be a nice way to handle this. Okay, so just gonna verify something super fast. Okay, so difference of cube works for cubic things added together as well as subtracted from each other. So I'll actually write it like this. So suppose we have a squared, oh no, not a squared, a cubed to the power of 3 plus minus b to the power of 3. Plus minus, it can be added, it can be subtracted. It'll work either way. Okay, so if we have a cubed plus minus b cubed, we know that the result is going to be a plus minus b. Multiply that by a minus plus ab plus b squared. Okay, now this is always positive. These two will be same sign. And these two will be opposite sign. No, not Sam sign. Hey, Sam's my dad's name. So, yeah, nice. And that will be opposite sign. Okay, so we know that in this situation, x is equal to a and 1 is equal to b. Now, if this was like plus 125, you would have to take the cube root of that first. So if it's 125, it would be b is equal to 5. Okay? Or, I mean, that's just an example at 125, but there are other types of cubes that you can just take the cube root before you set 1 to a and before you set 1 to b. I'll actually write that in. So cube root. This is what a cube root looks like. Awesome. So let's expand this out. So we got x3 plus x to the power of 3 plus 1. So that is equal to a plus b. So because they're the same sign for this one and that one, they're the same sign, so it's going to be just x plus 1. X plus 1. And because we know that a and b are x and 1 respectively. And then the next thing, oh, this should be a squared. My bad. Yeah. You kind of see how that pattern forms, right? Now here in the second term, we want to have the first one squared, so x squared or a squared. Now this is going to be opposite signs to what you see in here. Opposite signs. So what we're going to put in there instead of plus, we're going to put minus a times b. Well, what's x times 1? I think that's x. I know that's x. And plus b squared. 1 is b. 1 times 1, still 1. Okay, so b squared, that's 1. Now, could we factor this any further? Well, if we factor this, that means we'd have to find two numbers that multiply together that make 1 and add up to -1. I don't think we can do it. I don't think we can factor this out anymore, so this will be like the complete factorization of the problem, x cubed plus 1. So this is the key thing here that will really make your life easier is the difference of cubes equation. Keep that handy because when you see cubes, think of how you can possibly factor them out. Sounds good? Yep, and they came to precisely the same equation with precisely the same process of difference of cubes. There's also difference of squares. It's kind of a similar thing, but you know, that's a different topic for a different time. So the above solution is good. Okay, the next question is how do we write x, might be tough to see, but I'll just rewrite that, x to the power of 1 over 2 radical form. It's pretty rad, dude. Radical form. Okay, so this typically goes anytime you see a fractional power. Fractional powers. So how you convert this to radical form is that suppose you have x to the 1 over n. That's equal to the nth root of x. Okay, so in this case, 1 over n is equal to 2 in this case, so x to the power of 1/2 is equal to x to the second root of x. But since square roots or second root is so common, you actually don't need to write that too, because we just assume that it's going to be the square root if we don't see anything there. Now if we had something like x to the power of 1 over 4, you would need to specify that it's the fourth root, because we just do. Yeah. And you can go the other way too. Like if you have something under the root, you can just convert that to a fractional power, which might be easier for you to deal with in your calculators and such. But on different situations, you'll do different things. But yep, they got the situation right here. Yep. I'm just a little bit concerned about the general equation. Is very hard to read. Confusing. Final answer is right though. So this is it's pretty good. Yeah. Cool. So, what are inverse? The next question that we have today is, what are inverse operations? Let's actually just give a quick definition of inverse operations, and then we'll run through some examples. So inverse operations are basically an operation that undoes, like if you have a regular operation and then an inverse operation occurring like immediately after each other, they will get you exactly back to where you started. So they're kind of like they undo forward operations. If happen one after the other. Okay, so an example of an inverse, we can start at the very simplest inverse operations, and then we can like escalate up to some more higher intensity inverse operations. So the simplest one I can think of is addition and subtraction. Addition and subtraction. Now they're both inverse operations of the other one. So addition is the inverse of subtraction, and subtraction is the inverse of addition. So an example, if we have like x plus a minus a, minus a, that's equal to x. And that is because the plus a and the minus a, these are inverse operations, neutralize each other. Okay, so yeah, this will be useful in a lot of different areas of algebra. If you know the inverse operation, you can send things to like the other side. Okay, and the next pair of inverse things we know is multiplication and division. Multiplication and division. So if you divide by something, it's the same as multiplying its reciprocal, which is an interesting thing of looking at things. So if we do like a divide by b, that's the same as a multiplied by 1 over b, which is the same as a over b. Okay, so if you had anything, perhaps x as just like an anything, if you multiply that by a and then divide by a, you'll get x. So if you want to like neutralize something that you multiplied in, you divide the same thing out. And a nice thing to know is that like x over x, that could be anything divided by itself, is equal to 1 as long as x is not 0. 0 is the only exception, because dividing by 0, that breaks the rules. You can't divide by 0, never. If someone tries to say, hey, you want to try dividing by 0, you tell them, no, get away from me. That is not proper math. Okay, so multiplication and division are inverse operations of each other. Now, the next pair, this gets a little bit more intense, is powers and roots. And roots. So I think the thing that we're probably most familiar of or with is like the square root of something to the power of 2. That will be the same as just x. So the root and the power are kind of like inverse operations of each other. To undo the root, you square it. Now the order matters a little bit because the result of the root is going to be plus minus, so that's a little bit complicated, but a lot of the times you're able to just you can kind of tell from the context of your question if it's going to be either plus or minus. Okay, but it doesn't just have to be like powers of 2 and roots of and square roots. Like a more general thing would be like to the power of n, the nth root of x to the power of n, that's equal to x. So if you want to undo a root, raise it to the power. Okay, and I think the last one that I might want to mention is logarithms and raised powers. So the thing with logarithms and raised powers is that they also kind of they're able to neutralize each other. So the general equation is that a log of base of x, if that is the power of the base, that means it's equal to just x. So if you're trying to pull something out of its logarithm, set it as the power of the exponent. And it works the other way as well. So if you have like, I don't know, base, let's just call it base b to the power of x, and you're trying to get the x out, you can just hit it with the log of the base. And that will tell you the x. Okay, so these are just a couple of examples of inverse operations. The deeper you go into mathematics, you'll see like in calculus, you got integrals and derivatives that are inverse operations of each other, and then you also have like some matrix operations like transpose and transpose for like linear algebra, but that's a lot deeper than the stuff that I think is related to maybe the audience that is looking at this question for now. So yeah, these are just some of the inverse operations of each other. It's just like if one can undo the other. Addition and subtraction, inverse relationship with each other. Multiplication and division, same thing. They're related to each other. They're inverses. Powers and roots, logs and raised powers. I don't know if raised powers is maybe the best way to describe it, but you kind of see what you do. You got to just like put that as the power of the base if you're trying to pull something up the log, and if you just take the log of something to the power of what you're trying to find, you just you'll get it. Okay, sounds good. I guess they're showing it in a little bit of a different order. I'm not sure if additive property is related to inverse. Oh, I guess it kind of is. Yeah. So the above solution is good. Oops, sorry for that. Okay, the next question that we got on the menu today is what is the square root of negative, where is the square root of negative 4? Yeah, so that's this, negative 4. Okay, so the first thing that might be a red flag is a lot of the times you're saying like, oh, never take the square root of a negative number. Well, that is true, but also not true. Because I need to tell you about something. So we have something called I, which is the imaginary number or the complex number. That is equal to the square root of negative 1. It's not a real number. You can't count to I. You can't say like, how tall are you? I'm I centimeters. Imaginary. It doesn't make sense. But this is like, we're entering the complex domain of numbers, so because of that we're going to have an I term. Okay, so if I is the square root of negative 1, with some other properties that we know about roots, we know that this is equal to square root of 2 multiplied the square root of negative 1. No, not the square root of 2. I'm tripping. The result is 2, but it's actually the square root of 4. You see how we can factor out, like negative 4 is just positive 4 times negative 1. We can factor them out of each other and then keep them under separate roots. Okay, now we know that negative 1, the square root of negative 1 is I. So that's equal to negative 4 times I. Keep in mind, I is not plus minus. We'll get to that in a minute. And the square root of 4, well, what multiplied by itself gives us 4. 2 times 2 gives us 4. Negative 2 times negative 2 also gives us 4. So we do need the plus minus 2. Equals plus minus 2. And that's multiplied by I. So this is equal to the square root of negative 4. Plus minus 2I. Later on you'll see like why imaginary numbers are useful. If you go into like electrical signals, electrical AC signals, you'll see a lot of complex numbers. If you go into like more advanced areas of physics, this will also be very useful. It's very cool stuff. So now that you know this, if someone says what's the square root of a negative number, before you might have said like square root of negative number, not a chance. That's not math, but it is math. Now you know the answer. Just factor out negative 1 out of the negative thing, and just basically you just multiply by I, and then take the square root regularly. Don't forget the plus minus. If you forget the plus minus, it's going to be a lot of minuses that you're going to feel on your marks. So keep in mind plus minus, never forget it. Now, the final solution is correct. Correct. Step 3. Needs, should have the plus minus before the 2, not after. Yeah, but the final solution is good. Okay, so the next question that we got today is, what is a complex equation? A complex equation, also known as a complex number, I'll write that out. They have the following format. They're gonna look like this: A plus B times I. A and B, those are real numbers. So, sometimes they just say like capital R with like, you know, the fancier R, but I'll write it out: real numbers. So it could be like 1, 2, 3, 3.3, pi, the square root of 2, negative a billion, whatever number you like, as long as it's real for A and B. And I, that is equal to the square root of negative 1. Now this right here, this is like the fundamental part of complex numbers and complex equations. When you see an I, pretty much just treat it as if it's like a variable, or like you can't really or just know that it's like the square root of negative 1. It's an imaginary number. You can't really just incorporate that into like a single real number. It has a real component, so A is real component. B is the imaginary component. Okay, now that's essentially what a complex equation is. It's going to look like this. B could be a negative number. So, I mean, this is just as valid as A, or it could be like negative A minus B I. Or like, as an example, like minus 9 plus like minus 9 minus 8I. That would be a valid number, or a valid complex number. Jeez. Let me just redraw this 8. So like negative 9 minus 8I, that's a perfectly valid complex number, even though you know, our equation is like this, because we have A is negative 9, B is negative 8. Okay. Now, complex numbers are useful in a couple of different applications, but they get pretty advanced. You might use them for phasors, for signal analysis. If you're planning on doing anything with like AC electrical circuits, you'll see complex numbers a lot. And the way that you use them is also kind of similar to how you use vectors. You might and vectors are used a lot in a lot of different areas of big brain world. So, you know, it's an important important concept to like wrap your head around. So yeah, the above solution here, they had an example. Maybe it'd be good to show off a negative version of that, but the above solution is good. Is good. Awesome. So that's a solution. Good. Oh, and that wraps up all the questions. Time flies when you're having fun, as the old saying goes. Okay, just gotta do some things, and then, yeah. So, those are all the questions for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button below and ring the notification bell if you're a super fan. If you'd like to submit your own questions, please visit the video links in the description below. And remember to leave a like and comment, and share this video with your friends if you really liked it. This has been Millan from OneClass, and I hope to see you again soon. Have a good day!